So we're going to review what we did last time regarding the exterior algebra, and then continue with a few new facts. Now, always starting with our vector space V, we know we immediately get the dual space, and the dimensionality of V equals the dimensionality of the dual space, which we'll call N. And from this, we can create our one forms, because the one forms are elements of the dual space. So we can create one form, say alpha and beta, where of course alpha is going to equal alpha mu d, it's got a covariant component, right? Alpha mu dx mu, and beta would equal beta mu dx mu, like that, where those are, of course, dummy indices. And then from here, we can start creating our exterior power spaces. And we know that we start with the second exterior power would be anything like alpha, wedge, beta. And now look at alpha, wedge, beta. There's only two forms wedged together. But, of course, this breaks down just like it ever would, and we would get alpha mu dx mu wedge beta nu dx nu, which would give us alpha mu beta nu dx mu wedge dx nu. And now we come to this issue about how all this wedging works and what kind of notation we use. We know that this thing here is essentially restricted to, well, it's in principle, the only unique ones would be conditions where mu was less than nu. Of course, that's arbitrary. We could have restricted it to the occasions where nu was greater than, or nu was less than mu, right? We just induce a minus sign if we did it that way. Or we can leave it completely unrestricted and then just force, we can leave it completely unrestricted and understand that we're going to be double counting, right? So there's a few options here, and it really does depend on the context of the books you're reading, which one they use. But ultimately, the point is that any two-form, and that's what this would be a two-form. Any two-form would ultimately be a mu nu dx mu wedge dx nu. And here, a mu nu would be presumed to be anti-symmetrical, and if we use the other notation, the other condition where we force mu to be less than nu, sometimes we indicate that this way. If we don't and we allow it to go through everything, we will put in a 1 over factor of 2 factorial, because it's always going to be 1 over p factorial, where p is the p form, whatever p form you're dealing with. In this case, it's 2. And then we don't use these lines, right? And it's just mu nu, but we know mu nu is going to be a mu nu is going to be the opposite. Well, we know that a mu nu is going to equal minus a nu mu, and that's going to be enforced by the antisymmetry of those guys, which of course is what induces the presence of the 1/2. Anyway, so there's a couple different notations for those two forms, and then this process can be extended indefinitely to produce p forms. Oh, by the way, if you can take a two form and write it in the form, this form, that's nice. It's a nice simple two form, right? Any two form that can be simply expressed as the product of two one forms is kind of nice. It's given a special name, but likely it doesn't have to be that way. Ultimately, now we can now create alpha, wedge, beta, wedge, gamma, where gamma, of course, is just another one of these things. And that becomes a 3 form. And then, of course, alpha, wedge, beta, wedge, gamma, wedge, delta, 4 form, etc. And then we also understood that these guys can live in their own vector space, and that was a really important discovery from our last lesson, that these guys live in a vector space called the second exterior power of the covector space. This guy lives in the third exterior power of the covector space. And this guy would live in the fourth exterior power of the covector space. And then the one forms themselves live in the first exterior power of the covector space. So that first exterior power actually equals the covector space. And then ultimately you get the zeroth exterior power of the covector space, and that's going to equal whatever bin of real numbers is defined on the covector space itself, which in our case will just be the real numbers. So, and then this can go on indefinitely. However, it turns into zero after the level of the exterior power exceeds the dimensionality, right? So this will go all the way to the nth exterior power of the covector space. And then you will have alpha, wedge, beta, wedge, gamma, wedge, delta, wedge, say epsilon, where you have at most n of these. And then each of these vector spaces has its own dimensionality, and the dimensionality of the pth exterior power of the covector space is always given by n factorial over p factorial n minus p factorial. And what's really important to see here is that the pth exterior power space, let me write that better. The dimensionality of the pth exterior power and the dimensionality of the n minus p exterior power, these guys have the same dimensionality, right? If you plug in p and n minus p, if you put in n minus p here, and then you get n minus p, which of course is p, and this thing just flips, and so it's the same. And that's kind of important because we're going to see soon that what we're going to discover is that there's going to be an isomorphism, well, a mapping, let's call it. I mean, isomorphism is really the wrong word here. There's going to be a mapping between, say we had in 0, 1, 2, 3, 4, 5. Say you had 5. Say that the dimensionality of the underlying space was 5. So you have 5 different exterior power spaces. We're going to see that there's a one-to-one mapping here, there's a one-to-one mapping here, and there's a one-to-one mapping here. And so we're going to talk about that a little bit more today. What else did we learn from last time? Well, let's see. We also learned that given the vector space and its dual, that the basis of the dual space using the coordinate basis is also the basis of the first exterior power, right? We understand that because it's the same, these two are the same space, so we have to really think of it that way. We also learned that the zeroth exterior power is going to actually equal the set of the bin of real numbers, or functions on the manifold that give you real valued answers if you're dealing with a field, and I'll try to talk about that a little more later. And then we learned some basic rules, right? If we have alpha and beta that are elements of the first exterior power, we know that alpha wedge beta is minus beta wedge alpha, and we know that alpha wedge alpha equals 0. Now be careful with this. Alpha wedge alpha is 0 when alpha is an element of the first exterior power, if it's a one form. If alpha is a one form, any one form wedged with itself will give you 0. But that's not necessarily true for higher forms, right? So just keep in mind, because this is a very familiar thing to see, and it's a mistake to interpret it to be true for higher forms. But it is true for one forms, And between these two things and associativity, alpha wedge, beta wedge, gamma equals alpha wedge, beta wedge, gamma, right? Between those two and associativities, we know that any string, alpha wedge, beta wedge, gamma wedge, delta, in any string of wedge products of one forms, whenever any two are the same, no matter where they are in the string, this combined with this will allow you to realize that this thing is going to be equal to 0, right? Whenever any two are the same, you're going to get the whole wedge to be 0. And you could work this out. I mean, you could do every anti-symmetric combination tensor product. You could make this a massive tensor product, right? Alpha tensor product, beta, etc., plus, beta tensor product alpha, and you do it for every what we call odd permutation, and you use the right sign. Oops, this should be a minus sign, for example. If beta and alpha were the only two that were changed, it would be a minus sign. But we'll talk about that in 1 second. But you could work it out, and you would see that it will all end up being 0. And everything will cancel out. So we learned about that, and we learned also about how the signs change. And if you flip any two, right, if you exchange any two, well, in this case, you would have to change that to epsilon, right? If you change any two, the sign is going to flip. And then if you change any other two, the sign will flip again. And if you change another two, the sign will flip. And you can change two back, say, and then, every number of interchanges, the sign will flip. If you have an even number of interchanges, the sign is positive. If you have an odd number, the sign is negative. And the way you usually see this written in books on this subject would be more like this. You would write a one form down, say alpha sub 1, wedge alpha sub 2, wedge alpha sub 3, ... wedge alpha sub p. Right? So this would be a p form, right? Now, in this case, the subscript is just to indicate different one forms, right? I want to make a distinction between these different one forms, right? These are all different one forms. These subscripts have nothing to do with the spacetime indices. For example, alpha 1 should really be considered as alpha 1 mu dx mu, right? So the 1 is actually part of the name of the one form in this instance. So if I create this wedge product p form of p different one forms, then the way most textbooks will write this down is this equals the signature of sigma of alpha sigma 1 wedge alpha sigma 2 ... wedge alpha sigma p, where sigma is a permutation. Sigma of some integer I equals some integer j, where j is an element of 1 through p, right? And you're not expecting sigma I to equal sigma k unless I equals k, right? So you're expecting it to be it's going to be unique for each integer, and you're just basically reshuffling these indices, right? These indices, you're just permuting them in some way. And the signature of the permutation is either +1 or -1, right? That's what the signature of the permutation is. And it's +1 if there's an even number of interchange that gets you the permutation, and -1 if there's a odd number of permutation, sign changes to get you the permutation. And actually that gives us a way to write down an arbitrary tensor product, for example. For example, we could write alpha 1 wedge alpha 2 wedge ... alpha p equals the sum over all permutations, right, over all permutations of alpha permutation on 1, tensor product alpha permutation of 2, tensor product alpha permutation on p, and this whole thing has to be multiplied by the signature of the permutation. And that is the fancy way of defining these strung together wedge products. You're doing it over every possible permutation, and you're creating this tensor product, and you're multiplying it by the sign of that permutation. Now let's think of these guys in terms of fields, right? Form fields. Not a complex concept, because we already understand tensor fields and vector fields, well, and vectors being tensors or tensors being vectors. We understand those fields, but the idea here is still the same. So we can have a zero form field, and let's imagine let's see, a space of, well, let's try n equals 4. Let's see if I can pull off n equals 4. But a zero form field is going to be some function of the coordinates, where this function is a real valued function, right? So now, instead of the zero form being just a real number, it's now a function of the coordinates, but it's a real valued function on the spacetime. That's what makes it a field. Then we have our one form fields, and here we would write that as ax mu, some function of spacetime, times dx0 plus bx mu times dx1 plus cx mu dx2 plus, you see, dx mu dx3. So now I'm using shorthand, right, where I don't write out all four coordinates, right? But they're functions of spacetime. So that would be a one-form field. A two-form field will be something like px mu, but now it'll be dx0 wedge dx1 plus qx mu dx0 wedge dx2 plus rx mu dx0 wedge dx3 plus sx mu dx1 wedge dx2 plus, for s, I guess, tx mu dx1 wedge dx3 plus q or stu, let's go with vx mu dx2 wedge dx3. I think I've got them all. How many should I have? Well, I should have c 4 choose 2, which was 6. So I should have 6. Let's see, I have 1, 2, 3, 4, 5, 6. So that's all of them. And then you see these are acting as the basis vectors, right? And so we have a 6-dimensional, but it's a two-form field because the coefficients now are functions on the spacetime. And then we should have a 3-form field, which should have 4 basis vectors. Should be the same as a one-form field. And that's because C4 choose 3 is equal to C4 choose 1, right? And so that's going to be, I'll reuse some of these letters, Px mu dx0 wedge dx1 wedge dx2 plus pqx mu dx0 wedge dx1 wedge dx3 plus pqrx mu dx0 wedge dx2 wedge dx3, right? And so now if I tried to create, say I tried to create dx1 wedge dx2 wedge dx3 qrst x mu. Now I have 1, 2, 3, 4. So if I tried to create any other permutation of these, I would discover it's just some permutation of the ones we already have, and that would mean we would just sort of absorb that into the coefficient, right? In other words, if I added, say, plus QRST, say I added Vx mu, and I went with dx 2 wedge dx1 wedge dx3, what I would realize is that this is just a permutation of that, and in fact, in this particular case, it is an odd permutation, so I would just change the sign, and I would swap the indices, and then I would combine these two, and I would just create a new coefficient, S x mu, which was equal to T x mu minus V x mu, like that. So then I would just rename it. So I would just through relabeling, I can get it all right. So that's how this works. Okay, so those are the form fields. Then if I try to produce, and there's one more, a four-form field is going to be Px mu dx0 wedge dx1 wedge dx2 wedge dx3, and there's no possible other permutations that aren't, or other combinations of these that are it's C4 choose 4, which equals 1, right? So there's only one dimension in this space, and that's what it is, right there. So this covers, and this is analogous for every p-form. For n equals 4, we're done, right? Because if I try to make a 5-form field, I'm going to have to repeat one of these basis vectors, right? And that's not healthy. That's not going to work. Because if I repeat the basis vector, it goes to 0. So 5-form fields and higher are all 0. And this, so this is sort of explicitly writing out our fields. Now I guess this would be all in let's take the 3-form field, for example, would actually be T mu nu delta as a function of space-time, dx mu wedge dx nu wedge dx delta, like that. And then T, say, 0, 1, 2 would equal P x mu, right? So that's how this all compresses into the more standard notation. And that would, of course, equal minus T 1, 0, 2, and it would equal T 1, 2, 0, right? So that's how the sign changes on the indices would work. But this whole thing can obviously be expressed this way. We've gone through that many times. It's just nice to sort of see it written out explicitly. All right, now we're going to talk about an obvious operation, right? Let's consider a set of, say, let's say the second exterior power of V star. And then let's consider the third exterior power of the dual space. I keep trying to put an X in there. And if alpha say alpha is an element of the second exterior power, and beta is an element of the third exterior power. What's interesting is the first thing you have to understand is, which I'm sure is at this point no surprise whatsoever, the idea of alpha plus beta makes absolutely no sense, right? Two different vector spaces. There's no defined addition property that is allowable in this circumstance. You cannot add alpha and beta for the same reasons we've talked about before. Two different vector spaces can't be done, cannot be done. And likewise, if you're dealing with the vector space on, we have our manifold, right? We've kind of agreed that we've got to establish this architecture at every point in space-time. This architecture includes V star, all of the tensor product spaces you can create with V and V star that we've talked about. But now it includes all of the exterior powers, 0, 1, exterior power 2, etc. All of those exist as well. And in four-dimensional space-time, it's going to be 0 through 3, right? The exterior, 0th exterior power through the 3rd exterior power. It will exist at every point in space-time, and thus there will be these exterior power space fields all over the place. And but just like any other, the exterior power, the 0th power to the 3rd power exterior power fields, if the ones that exist here can't be added or compared to the ones that exist there straight up, because they're different vector spaces. So, however, the wedge product, much like the tensor product, can take two exterior power elements, two forms, and create another form, right? The wedge product between form alpha and form beta, right, that is going to be another form. It's going to be a form gamma. But that form doesn't live in either of these two spaces, right? That form will live in a different space altogether. And you can imagine, alpha is going to be written as alpha mu nu dx mu wedge dx nu, because it's a two form. And this thing, it makes perfect sense to wedge it with beta gamma delta epsilon dx gamma wedge dx delta wedge dx epsilon, right? And you can do that wedge very logically because everything is linear, because in the end all of these guys are tensors and we know that they're linear. So we can now create alpha mu nu beta gamma delta epsilon by pulling out these coefficients, and then creating dx mu wedge dx nu wedge dx gamma wedge dx delta wedge dx epsilon, like that. And this guy is a 5 form. Well, this whole thing is a 5 form, right? And that's great, except for the fact that if n equals 4, for the dimensionality of our underlying space is 4, then this whole thing equals 0, right? But if it was equal to 5 or higher, then that's not true. It wouldn't equal 0. So the whole point is that a P form wedged with a Q form equals a P plus Q form, right? And that's really good, because the wedge is a map that takes P, it's a map that takes P and well, it's a binary operators, right? So it needs P and it needs Q, and it takes it to P plus Q. I guess that's one way to say it. So you can actually create what we're going to call the exterior algebra. But much like the tensor algebra, which we discussed in the section on algebraic structures, an algebra requires a vector space plus a multiplicative monoid operation that stays within the vector space. But the problem is this doesn't do that, right? This guy here goes from, well, even if it took two operators in one vector space, right? Even if I took a P form and wedged it with another P form, right? Where both of these actually come from the same vector space, right? I'm still going to get an element of a 2P form, right? So this operation is not closed inside the appropriate exterior power. So we can never really turn these guys into algebras using this operation, at least, right? So what is it that we do to create the exterior algebra? Well, we're going to create a new set, right, where we don't put the little p up there, and we make it look like this. And what it is it is the massive direct sum of all of the individual exterior algebras. And that massive direct sum, now we can turn into an algebra using the wedge operator, because, so this direct sum, what does that actually equal? It equals this. I'm gonna omit this part now. We all know that when I talk about the exterior powers, for right now I'm talking about the exterior power of just the dual space. So these are P forms. By the way, this logic works, and I think I mentioned that last time, this logic works for any vector space. You can create the exterior power of any vector space, but in order to call it a form, right, we are always referring to the covector space of some underlying vector space. Otherwise, we call it a P vector, right? So we have P vectors, that would be this space, and then we have P forms, which would be always this space, right? And so this guy here is going to be the direct sum of that plus that, direct sum to dot dot dot, direct sum, goes on forever actually. Of course, it goes on forever, but after k greater than n, they're all zero, right? So unlike the tensor product space, which was, we could say that the tensor algebra on V star, say, would have been the direct sum over k of t 1, well, let's see, 0, 0, well, it would have been t 0, say, k, right? And that would have been, well, it would have been, let's see, it would have been t, the 0th one, which would have been the bin of real numbers, direct sum, the vector space itself, or the dual vector space itself, plus the dual vector space, tensor product, the dual vector space, direct sum, I'll just do one more, direct sum, etc., right, where we just keep adding another tensor product until it goes on forever. And this can get unlimited big. There's no limit on this. So this tensor product space that we defined in the algebra goes on forever. This one does not. It terminates with k greater than n. Okay, let me erase this. How do I get rid of it? Hold on. I've forgotten exactly how to do this on my whiteboard. Okay, there. So now, and as a reminder, because it never hurts to remember, this set, right, this is a set, and it's a vector space. We know it's a vector space because we know the direct sum construction on vector spaces always yields another vector space. And this guy here is the set of all, basically, the set of all, what will it be? It'll be n plus 1 tuples. So it'll be the set of all multi-tuples where the first slot gets an element of sigma 0, so that'll be some real number A. The second slot gets an element of the first exterior power, which we might call, say, alpha. The second slot gets an element of the second exterior power, which might be alpha. Well, I don't want to write it that way because not all elements of the second exterior power can be written like this, right? Sometimes you have to write them like that, for example, right? You have to include a sum. Sometimes you have to do that. So I think, if I remember right. So I'll call that, say, B, and then you go all the way down to, say, Q, where Q is an element of the nth exterior power, right? And so all of these n tuples are the elements of this space, and of course when you add, it's a vector space, so you have to be able to add n tuples to each other, which of course is straight. You just add each, if I had two n tuples, I would just add them and I would produce another n tuple where I take this element, add it to the first element, and I get the element, the sum, and I would add alpha to beta, and I would get alpha plus beta, and I would add b to c, and I would get b plus c, and that's the sum. And of course, the identity is really easy. It's just all zeros, and so that's what the direct sum space of these guys looks like. And so now, when we understand that, an element of the pth exterior power wedged with an element of the qth exterior power is an element of the p plus qth exterior power, now we can actually use this operation as the multiplicative operation on this space here, right? And when we do that, as long as our rules are legit, as long as our rules are straight, we know that we can now multiply these individual elements with each other, and we just move them to the correct slot where they belong, the p plus q slot, if it exists, right? Because you could easily imagine overflowing into the zero regime, in which case it's just zero. So, so you can create this algebra on this direct product space without any trouble, and that algebra is called the exterior algebra. So that is the exterior algebra. And it's totally linear, so it's so you'll end up with it's a linear product. This guy here is linear over the direct sums addition property. So that's the definition of the exterior algebra. Now there are a few things you need to know about the wedge process as the operator in the algebra, and you need to know that if omega is a p form and if eta is a q form, let me use a small q, then omega wedge, I guess what is that? Is that an eta? Omega wedge eta, first of all, we know that that's an element of a p plus q form. We know that. But now, if we look at it, we know that ultimately omega is going to be, we can construct omega as omega alpha beta dx alpha, well, it's going to be omega alpha beta dot 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 dx alpha wedge dx beta dot dot dot, and that thing is going to be wedged with eta gamma delta dot 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 dx gamma wedge dx delta dot dot dot. Okay, so you can imagine that's what this is going to look like if we substituted in a sample in our coordinate basis. And you can see that, imagine I was curious about eta, wedge, omega, right? And it's really not a problem. First of all, the coefficients, they just pop out linearly. So what I'm left behind with is this form wedged with this form here. And I see that if I'm going to take this dx gamma and I'm going to move it to, say, the front, I'm going to have to interchange it with dx beta. Well, I'm going to have to interchange it with every one of the one forms in this string of p long, and finally interchange it then with beta, then with alpha, and finally it'll get out front. And that's going to require p interchanges. And then if I take the next one that's left behind, which would be delta, x delta, and I want to move it to just in front of, so now I've moved, I guess I should actually do this, right? So now I've created omega, alpha, beta, eta, gamma, delta, pulled those two things out because they're linear, and I've moved this dx gamma to the front. So I've moved this dx gamma to the front, and it's taken me p interchanges to do that. So I'm going to be left with minus 1 to the p power, right? Because if p is odd, I'm going to be left over with a minus 1. If p is even, it's going to have no effect on the coefficient. So I do that, and now I've got the gamma out in front. And then this is dot, 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 and now I have dx delta here, right? Wedged with its buddies. Now I want to move dx delta to this spot right here, right? So I'm ultimately going to get dx gamma wedge dx delta wedge dx alpha wedge dx beta wedge dot 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 with whatever's left behind. And eventually I do that because remember there are q of these here, right? There are q of those and there are p of these. So I do this q times, right? And ultimately the sign alpha, beta, gamma, delta is going to be minus 1 to the p when I moved gamma, but then I'm going to do that again for every one of these guys q times. So it ends up being minus 1 to the p times q sign changes. And that's the rule. So the rule is omega wedge eta equals minus 1 to the pq of eta wedge omega. All right, so that's this rule here. That's the origin of that's the way these things commute or don't commute. If they don't commute, they anti-commute. But you'll notice if two things don't anti-commute, then we have this problem, right? Omega wedge omega will equal minus 1 to the p squared omega wedge, omega wedge omega, where we've interchanged omega and omega. So with itself, in a sense, right? We pretending we're doing this sort of fiction of commuting it with itself. So if p is even, then that becomes minus 1 to the 2p squared, which is going to be even, which equals omega wedge omega again. And if p is odd, it'll be minus 1 to the, let's see, 2r plus 1 squared, right? Which is actually always going to be odd, right? That's always going to be odd. So that will be minus omega wedge omega. So in the second case, in the p odd case, we have omega wedge omega equals minus omega wedge omega. But in the even case, we don't have that. We just has equals omega wedge omega. So the point of all this is that the wedge product of a p-form with itself is equal to 0 only when p is odd. Okay? When p is even, a wedge product of a p-form with itself is not necessarily 0. And we can see that through the logic of this rule here. Now there are two important little results we have to know that I'm not going to prove, but you can find the proofs out there. It basically has to do with the change of basis. We always like to understand about change of basis when we work with our various tensor objects. So we got to imagine that we have, I'm going to write them down as one form. Say we have one forms E0, E1 to EK, right? And these are just a bunch of one forms in V star. A change of basis for one forms, we could go from the E basis to the E hat basis, and we could have E hat 0, E hat 1 to E hat K. And these, of course, are all also members of the first exterior power. And the relationship between the two will be this. E hat of, say, alpha is going to equal some matrix. We always call these transformation matrices lambda before, so I'll keep that because there's really no confusion here. And it's going to be E hat alpha will be alpha beta E beta, right? So that's a linear transformation change of basis, your standard change of basis. So the interesting rule is that if the dimensionality of V star is n, we can form the vector space, the nth exterior power, which we know has dimension of 1, right? The dimension of this equals 1. It always equals 1 when the dimensionality, when the exterior power equals the dimensionality of the space in question, you get a dimension of 1. So I can write down E hat 0 wedge E hat 1 wedge E hat I guess E hat, we got to go all the way to n, right? I want to go all the way to n in this example. So, well, the dimensionality is n, so I think I want to go to n minus 1, right? Okay, anyway, and that's because I started with this darn 0. So, but that is going to equal, let me move this out of the way, that is going to equal lambda well, I can tell you, so each of these basis vectors have to be adjusted. So it's going to be E0 beta E beta wedge 1, and I'll just use the same dummy index. Well, no, I can't really do that. Well, yeah, I can. Beta, beta, dot, dot, dot. You know, wedge lambda n beta E beta, like that. And so this is our conversion, right? This is our conversion for each of these basis vectors by the linear transformation lambda. The point is that this thing is going to equal the determinant of lambda times E0 wedge E1 dot 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 all the way to En, wedge En. And that's really interesting because this lambda is a matrix, right? And it does have a determinant, so that makes perfect sense. What's interesting, it's the only number you can really form, the only single number you can really form out of a square matrix is the determinant. That's the only reliable one that means anything. And it's interesting that this change of basis process yields this determinant. But at some time, in some sense, it's really logical because, first of all, this is a one-dimensional vector space over here, or an element of a one-dimensional vector space, because it is the nth exterior power we're dealing with, right? We went from 0 to n. We're doing the nth exterior power. So this is an element of n where the dimension of v star equals n. So it's one-dimensional. So ultimately, being one-dimensional, in the end, any linear transformation of the basis vectors, right, can only return to you a number times the same basis, right? And there's only one way to generate a number out of a linear transformation, and that's to take its determinant. Now, you can actually prove this very rigorously, but I'm not going to go through it because it's actually kind of a tricky little proof that involves taking a lot of matrices and things, but it's a very interesting proof. There's a good one involving an induction proof, but ultimately this determinant here is exactly the same determinant that we learned from linear algebra in the past. And also what's interesting is you can do this without going to the full n dimensions, right? You can ask, well, what about this? What if I want E hat 0 wedge E hat 1 wedge E hat 2, and n is much greater than 2. And now you actually have and now, so this is going to then be lambda 0 beta E beta wedge lambda 1 beta E beta wedge lambda 2 beta E beta. And now the question is what matrix comes out here for that linear transformation? And the answer is actually interesting. It's a matrix where it's a generalized determinant, right? It's a generalized determinant where, remember, a determinant is actually based, this guy here is always going to be an n by n matrix, right? Any linear transformation is going to be an n by n matrix. So with that in mind, you have to produce a different number from only 3 of these n by n matrices. And it turns out that matrix ends up being in this case it would be a 3 by 3 matrix of cofactors, of the various cofactors buried inside the n by n matrix. And that's another determinant fact. It's a little bit off of our main line of development here, so I'm not going to go into it. But you can create a generalized determinant, which can be traced back to linear transformations of these exterior powers. What's also interesting, let's see if I have room for this, is that if V has an inner product, right? And I think we did a notation for the inner product like this. So we had a vector V and a vector W, and this inner product is an element of R, right? If V has an inner product, then there's going to be an inner product induced on all of the exterior powers on V, right? Any exterior power of the vector space V will also have an inner product. And the determinant sort of shows up nicely here as well. So what would an inner product on this space kind of look like? Let's say we called that alpha, beta, and we put a little, not V, what am I trying to say? We should put a little I'll put a P here, right, to indicate that it's the inner product on this vector space. So we have an inner product assumed on V, the underlying vector space, and I guess, for example, the dual space could have an inner product that's induced from the vector space. So let's do it this way. We have an underlying vector space with an inner product, which of course induces an inner product on the dual space, right? And once you have that, you will ultimately end up with an inner product on the exterior power of the space of all P forms, okay? And that interior product we're going to call this with a P. So alpha is a P form and beta is a P form. So you can imagine if this was a P form, you would have something like, if you had a simple P form, which you could write down as alpha 1, alpha 2, alpha 3, that was the word. A simple P form can be written as P copies of some one form out there. So if you have a simple P form and another simple P form, beta 1, wedge, beta 2, beta P, right? They both have to have P. You can't do this with a P and a Q form because you're talking about an inner product, and an inner product only exists inside a single vector space, and all the single vector space is occupied entirely by P forms. So you have the inner product of two P forms. So what does it turn out that that's going to actually be? Well, it's interesting. It is the determinant of a matrix. And the elements of that matrix are going to be, because we're trying to generate this inner product, knowing this inner product. So it's going to be alpha 1, comma, beta 1, alpha 1, comma, beta P, alpha P, comma, beta 1, alpha P, comma, beta P. So I can form the inner product that's induced on the exterior power space by the inner product from the original vector space is this guy right here. Is this the determinant of the matrix? Now notice all of these are going to be real numbers, right? Because these are inner products, and these are the inner products defined here, right? The inner product defined on the underlying vector space. So those are the inner products defined here. You form that matrix, take its determinant, and that is how you form a real number from two elements of the pth exterior power. So this rule is interesting to see, and again, it can be derived by just breaking these things apart and piecing them back together, because everything's linear, right? Everything has to be linear, and it's that linearity that allows you to break this apart, reassemble it, and create and exploit this to create something like this. All right, so now we're going to study a very important idea called the Hodge star operator, which is really getting back now to this idea of operation, which is getting back to this idea of how to link up the pth exterior power with the n minus pth exterior power. Now you remember when we first looked at this, when we first studied the vector space V and its relationship to the dual space, we understood that although these are related, and although we've invented a basis whereby we knew that the dual space mapping mu operating on the basis vectors, and now again in the coordinate basis nu, was going to be delta mu nu, we understood that this connection of defining the dual basis in the dual space was an arbitrary idea. There was no real canonical way that forced us to take a certain vector in V and associate it with a certain vector in V. We do this because we find the delta function to be convenient, but convenience is not canonical. And therefore, we needed something more to establish this one-to-one correspondence. And that thing more was the inner product. And I think I was using parentheses back then for the inner product. So it would be V, W, both elements of the vector space V is an element of the real numbers. And once we had that inner product, then we could establish this correspondence. A very similar idea exists here. We have two separate vector spaces. There's really no relationship between them except for the fact that they both have the same number of dimensions. Now, it is true that if you have vector spaces with the same number of dimensions, then they are isomorphic. You can create a one-to-one correspondence between them. You can make a map between them. They're essentially the same vector space in many ways. But to pick one out requires something more. And as always, we're going to go back to the underlying vector space and its underlying inner product, just like we did back here. In order to define an inner product on the pth exterior power, we leaned on the inner product that existed for the vector space, and that inner product flows through this whole situation and gives us an induced inner product. You could, by the way, invent other inner products for this space, but the one that's actually induced by this is this inner product here. But now we're looking at something different. We're looking at an inner product on here, not to define an inner product on this space or an inner product on this space. It's already defined. There is an inner product here and there is an inner product here. That's important, and we've defined it, right? This is it. But now what we want to do is create a one-to-one correspondence between the two vector spaces that have the same dimensionality, right? And so how would that work? Well, let's break it down. If I took an element from this vector space, say I take the element alpha, and then I take an element from this vector space, an arbitrary element beta. Let's stick with a fixed alpha and we change beta up, so we can pick any beta. From these two things, I can produce alpha, wedge, beta. And alpha, wedge, beta, we know is going to come from the nth exterior power. And why do we know that? Well, we know that if this is the pth exterior power and this is the n minus pth exterior power, this is going to be the p plus n minus pth exterior power, which of course is just the nth exterior power. And that's important because this guy here is one-dimensional. Right? Its basis vector would be dx0 wedge dx1 dot 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 wedge dxn minus 1. So this is a way. So starting from this point, we take any element of p and any element of n minus p. We're going to produce an element of n, which is one-dimensional. So we know that no matter what this guy is, it can always be expressed as dx0 wedge dxn minus 1 times some real number. In that real number, since we're holding a fixed, I'm going to attach it to a, but it's going to be that real number is going to obviously depend on what b we choose. It depends on what a and b we choose. So it is a function of a and b, but we're going to hold a fixed, so this is a real number which is dependent on which a you hold fixed, but it's also dependent on b. And this is common, by the way, and it actually comes up a lot in different forms of analysis where, truly this is a function of a and b. A and b can both be considered as independent variables here, right? But we are going to just play around with b as an independent variable, so I'm going to write this in a way that's suggestive of that. So I write it this way. All right. So, and that happens actually quite a bit. The naming functions after a parameter. So we would tend to call a parameter and b an argument. But the truth is a parameter can be changed. So in some sense, a parameter is an argument. So it's the way you want to sort of look at it is the way you want to write it. So we're going to write it with that alpha down there for right now. Okay, so okay, so so we know that this is going to be a real number. Well, now my question is everything being linear, we can assert that that there exists an element of this vector space here. Let me put it in red. There exists an element in this vector space that I'm going to call alpha star. And that's really alpha Hodge star. And alpha star inner product beta is going to be the value of f alpha beta. And this has got to always be true. It turns out that we can always find a member of this. I don't want to call it the dual space, because this is a vector space and its dual space would be a map of elements of it to the real number. So I don't want to call this the dual space, but it's the Hodge dual space. Why don't I call it the Hodge dual space? Because this thing is called the Hodge operation. So this is the Hodge dual space, or the Hodge space. How about that? It's the corresponding space of the same dimensionality, n minus p. And inside there is the Hodge dual of any given number alpha, such that if I take any element out of the Hodge space and form the inner product of that element with the Hodge dual. Now remember, the Hodge dual and the element that I'm multiplying by, the argument here, come from the same vector space. So this inner product takes two vectors from the same vector space, because it's an inner product. So I can form that real number, and that real number is going to always be the result of just wedging the original alpha with any arbitrary member here. And that idea, that object, is the Hodge dual. So we want to learn how to find the Hodge dual of any underlying exterior power P. So how might we do that? So we might start, as an example, let's take lambda, or the second exterior power, and the first exterior power. I got to keep low dimensions here, otherwise the proof or the demonstration takes a long time. And from the second exterior power, I might consider alpha to be just dx0 wedge dx1. And then again, I get to take an arbitrary element from the first exterior power. So that's going to be, I'll call that beta mu dx mu. And I'm going to form alpha wedge beta, which is going to be dx0 wedge dx1 wedge beta mu dx mu, like that. And so now I am going to be interested in showing this inner product, right? The inner product I want is the inner product of some unknown member of the first exterior power. So I'm looking for a one form that is dual to this. So I'm looking for alpha star is a one form. It's an element of the first exterior power. And I want it to be so that alpha star inner product with beta mu dx mu, right? I want that must necessarily equal, that must equal this thing right here, right? And so I can actually write that down explicitly. I can write, I'll replace this with an expansion, and that expansion will look like, let's see, it'll be a dx0 plus b dx1 plus c dx2. How about that? So I'm going to, I guess I have to make the point here that the underlying vector spaces we're dealing with are V, the dimensionality of V equals 3, right? So, and let me erase this side again. So that, and the reason that's important is because this has to be P, a P form, and this has to be an N minus P form. So in order for this to be N minus P form, I need to have 3 minus 2 equals 1, right? So that's where this 1 comes from. So there is your arbitrary 1 form, and this thing here is alpha Hodge dual. We don't know what it is, so I've written it out in total generality. But that Hodge dual blended together with some arbitrary 1 form is going to end up being the coefficient in front of dx0, dx1, dx2, right? Because that is what we meant here, right? That is this guy here, this inner product, actually is the coefficient on the basis vector of the single existing nth exterior power. So it's the third exterior power space, right? So this is the basis vector of lambda 3, right? So I need to form this inner product, right? So now I can actually figure that thing out by just taking B one time after another to be dx0, dx1, and dx2. And from that, I can calculate everything very straightforward because remember, this has got to be true for alpha star has got to work for any B, so it's certainly going to work for these basis vectors. So everything being linear, this is really easy. It becomes A dx, let's use dx0 first. So beta is dx0, so I'm going to insert it there. dx0, dx0 plus b dx1 dx0 plus c dx2 dx0, right? And then this guy here goes in the back. And now, understanding that it's very important for us to be dealing with an orthonormal basis, right? If we have an orthonormal basis, which we can have, because once we have decided that, once we've decided that this vector space, this underlying vector space has an inner product, once we decide that, this should have been a curve here, right? I think I'm using curves for my inner products. Once we've decided that, then our basis vectors, we know what orthonormality means, right? We know that dx mu dx nu equals delta mu nu. We've chosen that basis. And in the coordinates basis, it's already true no matter what. But we can always choose this orthonormal basis when we have our inner product. So given that our underlying basis, the basis we've chosen here, and these basis vectors are orthonormal, this and this go to 0. That and that go to 0. And so we end up with and then this equals 1. So we have A dx0, dx1, dx2 on this side, and on the other side we have alpha Hodge dx0, right? But what was alpha? Alpha was dx0, dx1. So we now have dx0 wedge dx1 wedge dx0. So we have all of that. So this thing here equals 0, which has to equal A dx0 wedge dx1 wedge dx2. So we've just shown that A must equal 0. All right, so how about B? Well, let's now take dx1 in there. Now we should get, ultimately, that we're going to end up with, if we go back, we can look at this. If I put dx1 in there, that term is going to go to 0. That term is going to go to B, and that term is going to go to 0. So I'm going to get B dx0 dx1 dx2 on this side, and then on the other side I'm going to get let's see, I'm using dx0 dx1, so I'm going to get dx0 wedge dx1 wedge dx1, which equals 0 because the dx1s are duplicated, and so this doesn't work, and so B equals 0. All right, so which leaves me to x2, right? And now I will just erase this so I can keep writing on the same slide because I've forced myself into a corner. And with x2, we're going to get, on the left-hand side, dx0 wedge dx1 wedge dx2. Well, that's good because that one is not 0, and that's going to equal C times dx0 wedge dx1 wedge dx2, like that. And so now I know that C equals 1. And therefore, I've now found that 0, and this is 1. So now I can say that the Hodge dual equals dx2. But furthermore, what I can say is that dx0 wedge dx1, that's the vector alpha, the dual of that is simply dx2. Now notice, this is our answer. And what's next, so this guy here, that guy is an element of the second exterior power. This guy is an element of the first exterior power. So the dual of the element of the second exterior power, the Hodge dual, not the dual, the Hodge dual. Remember, the dual is a different thing. The dual would map these guys to real numbers. The Hodge dual is a member of the n minus pth exterior power. Well, n is 3, p is 2, so it's a member of the first exterior power, which is, of course, what this is. So we've just solved for the Hodge dual of dx0, dx1. Now, I can do this for the others, right? I can write dx0 Hodge dx1, wedge operation. The Hodge dual is dx2. Then I can do dx0 wedge dx2, right? dx0 dx2, that's going to be, it turns out that's going to be minus dx1, and then dx1 wedge dx2, oops, sorry, Hodge dual is going to equal dx1, dx2. I'm just trying to run this through in my head real quick because you have to flip one. I got to make sure. I know we had to flip one here. This is going to be dx0 without a flip. Now notice there's no ambiguity about the use of the dual star operation here with the dual here, because this dual takes a vector space, which is a set. So this is sort of an a name on a set. And so it's a set of maps that take all the elements of V to the real numbers, like we've learned. This is a dual operation acting on one element of a set, namely an element of the second exterior power. And so there's really no ambiguity. So this is what creates the correspondence. But notice the correspondence can't be created at all without this inner product, right? We need to have this inner product to go through all of this math to find the dual. And now with this, now I can branch out. Now I know as usual with vector spaces, if I know something about the basis vectors and how things work on the basis vectors, everything being linear, I can say something about any vector in the second exterior power. So let's take any vector in the second exterior power. I'll call it A dx0 dx1. Remember, the dimension, and for this exercise, the dimension of V is only 3, right? And that's so I can just get through the demonstration smoothly. B dx0 wedge dx2 plus C dx0 wedge dx1 dx2. All right, so that's an arbitrary vector in the second exterior power space of V star. So if I now want the Hodge dual of that, right, I can, it's all very linear. The Hodge dual of that is going to be A times the Hodge dual of that plus B times the Hodge dual of that plus C times, whenever I have a C in front of a parenthesis, it always looks terrible. Of course, that's because I write like a 3-year-old child. The Hodge dual of that. And we know what the Hodge duals are. We know that this is going to be A dx2 plus, whoops, not plus actually, minus B dx1 plus C dx0, like that. And this gives us, well, and all of this gives us pretty good opportunity to make contact with another thing that we all know so well from elementary physics, right? We know from elementary physics that the cross product, E1 cross E2, right? You know, you got to use your right hand rule and you cross X into Y and you get Z, and that equals E3. And we know that E1 cross E3, right? X into Z, that gives you minus Y, so that should be minus E2. And you know X E2 cross E3, Y into Z, that gives you E1. And so this cross product actually mimics this Hodge duality, which is interesting, right? I mean, we've defined a cross product, right? We've defined in elementary physics, we define this operation called cross product, which takes two vectors and gives back another vector. That's not quite what the Hodge dual does. Well, in a sense, kind of the Hodge dual does do that, right? It says, say we take two, I say vectors, but we'll take two covectors, right? And say the operation is form the wedge product, take the Hodge dual, and you'll get another covector. So that does, in a sense, it's an operation that looks like this, right? Right? An operation that looks like that. That is a binary operation that takes two dual vectors and returns a dual vector. right? So in some sense, this is just like a cross product. However, what it really is it's a correspondence between these exterior power spaces, right? Where inside here you have the second exterior power, and outside here you have the first exterior power. But the mapping is actually the same. And in fact, you could say that E1 cross product E2 actually equals the Hodge dual. You know what? I think the Hodge dual, now that I think about it, goes on the other side typically. You don't put it on the right side, you put it on the left side. I think I made a mistake on that. I think it actually typically goes on the left side. But it's going to be E1 Hodge dual E2, or E1 wedge E2 Hodge dual. And for vectors in Euclidean 3 space, you know, the old engineering classes, if you have any friends who are engineers who have to suffer through this is their terminal understanding of vectors, is basically, you know, E1, E2, and E3. That's all they know, and they know these rules real well. But, you know, we physicists kind of go beyond it because we want to do this in 10 dimensions, right? Well, this doesn't work in 10 dimensions. That only works in 3 dimensions. However, this process actually does work in 10 dimensions. But that's the point I'm going to make in a moment. Let me not get ahead of myself. But you can now create this notion of a cross product. Remember, these objects, these unit vectors, sure enough, they're vectors in a vector space, you know, regular old Euclidean space, and the basis is E1, E2, and E3, right, which is x, y, and z unit vectors, sometimes given by x, y, and z hat, right, or sometimes given as I, j, and k in boldface, right, and the rules are I cross j equals k, and j cross I equals minus k, right, which exactly works in our definition, because if you flip these two around, you're going to change the sign. So the point being that we can now, these guys are vectors like all the vectors we've studied. And so we can create these operations that look like this. And those operations are actually forced upon us. The only thing we need is an inner product to make that work. And once we have that inner product, well, what about here? Do we need an inner product to make this work? And of course we do, because implied in this is orthonormality, right? So engineers and beginning physicists always have orthonormal bases, but you can't have orthonormality without an inner product. So the inner product's always implied, and once you have it, this is the actual formal operation that produces this cross product. Okay, so what have we done? I've demonstrated this notion here of the Hodge star operator, which in summary links every member of the pth exterior power to the n minus pth exterior power by exploiting, ultimately by exploiting the inner product on the underlying vector space, which is, in this case, is the case I demonstrated, which was from the second exterior power to the first exterior power. And I just did this calculation using this inner product to calculate a Hodge dual for each of the basis vectors. And once we had the Hodge dual for each basis vector, we were able to, by linearity, find the Hodge dual for any basis, any member of the basis space. So you always want to hunt down this stuff, right? You want to go into the pth exterior power, find the Hodge dual for each basis vector, right? Find out what that Hodge dual is in the n minus pth space, and then you can take any vector in the pth exterior power, and you can produce the Hodge dual just by substituting right in for the basis vectors. And this can be done for any set of powers, right? So it's important to remember that we can do this for, say I have. Let me go for it, right? Let me write down 3, fourth exterior power, fifth exterior power, sixth exterior power. How about we do 7 exterior power? So the underlying space, which we'll call V dual, we'll say that the dimension of V equals 7, right? And now we are able to, this correspondence is, these two would be corresponding, and these two would be corresponding by Hodge dual, and these two would be corresponding by Hodge dual, and these two would be corresponding by Hodge dual. So I can always create. We know that this is going to have dimensionality of 1. This is going to have dimensionality of 1. This is going to have dimensionality of 7. Therefore, I know this has dimensionality of 7. And then this is going to have dimensionality of 7 choose 2, which is 7 factorial over 2 factorial times 5. 7 minus 2 is 5 factorial, which is what? 7 times 6 times 5 factorial divided by 5 factorial over 2 factorial, which is going to be 7 times 3, which is 21 dimensions. So this one will have 21 dimensions. And then these two in the middle will have 7 choose 3, which is going to be 7 factorial over 3 factorial times 4 factorial, which is 7 times 6 times 5 times 4 factorial divided by 4 factorial, 3 factorial, which equals 7 times 5, which is 35. Whew. So 35, dimension 35. So now you need, if you were going to generalize what we did over here, right, where we did this calculation working through the inner product, right, this was the inner product on, this turned out to be the inner product on an orthonormal inner product on V star, which was lambda 1, right, because the Hodge dual lived in the first exterior power. In this case, say you were looking for the correspondence between this and this. So I would pick an element of lambda 2, and I'm looking for an element of lambda 5. So now I'm looking for something that looks like A alpha mu nu delta lambda eta dx mu wedge dx nu wedge dx delta wedge dx lambda wedge dx eta, and I need inner products on this space, right? And those inner products, they're not easy, but they're defined. We did define them, and they're defined this way, right? That's an inner product, say, on P equals 5. That's what it's going to be. It's going to be the determinant of a 5 by 5 matrix. So you can imagine how messy that gets, but it can be done, and it can be guaranteed to be done as well. So you can always find a Hodge dual for any vector in here. You can find its Hodge dual in here. So if I take, say, dx0 wedge dx1 out of this, I can find the Hodge dual of that, right? The Hodge dual of that is going to be something that looks like this, that we have to calculate sort of the hard way using this inner product as your basic rule. Okay, so that's what the Hodge dual is. So let's have a look at some other properties. For example, it's not just the cross product, right? So say I had, so let's go back to our Euclidean space, right? Our Euclidean space example. We have x and y and z. So we can always, and so this will be I, j, k unit vectors, right? Like that. So I can say that any vectors in here, any vectors in this Euclidean space, say I had a vector x and a vector y, I can say x cross product y, and I can I can now write that into new rules. I can say the Hodge dual of x wedge y, right? That's what that means. But I can do this for just about every single vector algebra expression. For example, I could say u dotted into x cross y, right? That turns out that's going to be the Hodge dual of u wedge x wedge y. And I can take there's more sophisticated ones, right? I can say u cross x cross y, right? And that one is u wedge Hodge dual of x wedge y. That's what that equals, right? So I just happen to know these formulas from having just recently worked through this. The point being is that all of these common things that we've used in vector algebra can be expressed in these terms if I just take the dimensionality of the underlying vector space to be 3, right? And as usual, I can form all of the results on the basis vectors, and I can still do all the calculations the same. All right, well, that's it for now. This was a long lecture, but it was not a hard one. I think I might even do one more on the exterior calculus, showing how it can be exploited to understand Maxwell equations. That's usually what happens. They usually explain Maxwell equations with the exterior calculus as a demonstration of what it's good for, and also explain how it generalizes things to higher dimensions. So maybe that next time.